Hello, welcome back to the video lecture series for Introduction to the Art of Programming using Scala. We continue our discussion of linked lists, and we're moving past the singly linked list to a doubly linked list. So the doubly linked list conceptually is very much like the singly linked list. If we look at an image of one, here's our singly linked list. Every node has the data that it stores and a single pointer to the next element. In a doubly linked list, as the name implies, there are two links. Okay, so each node now has the data that it stores, as well as, in addition to the next pointer, we have a previous pointer or a reference. So the first node stores a reference to the second one, but the second one stores both a reference going back and a reference going forward. The advantage of the doubly linked list, just right off the bat, is the fact that if I go to an element, I can delete this element from where it is. Whereas in the singly linked list, if I wanted to delete an element, I had to have its predecessor because the predecessor had the pointer that I needed to change. Here, I can be at this point and I can delete it because I have access both to its predecessor and its successor, the one before it and after it. In addition, I can walk backwards through a doubly linked list. Whereas the singly linked list is walking forward only, this one I can walk backwards as well. Now in our actual implementation, I'm not going to keep a head and a tail. And the reason I'm not going to do that is because I can use something that makes our code easier to work with. You might remember from the singly linked list that a lot of what added complexity to our singly linked list, close that one, was the fact that we had special cases for setting the head and the tail. So with things like here we have this special case for TL. We have this entire huge case for n equals 0 because it's going to change the value of head. This code really got a lot longer and a lot more complex because of the need to deal with those special boundary cases. And if we could get rid of those, it would be possible to simplify the code significantly. The reason we had them is because head and tail were separate pointers. They weren't a next pointer. Our normal code just dealt with next pointers, and it walked through nodes and next pointers, nodes and next pointers, and everything was happy. But anytime we had to change head or tail, that became special case code. It's possible to make a doubly linked list and make it so that it doesn't have a head or a tail. And we do this by making it circular, first off. So you can make your singly linked list circular. You just take the last node and point it back to the first node. It's a perfectly valid thing for you to do with your singly linked list. With a singly linked list, there are only a few applications where that's helpful. But for the doubly linked list, making the list circular is remarkably beneficial. And to see why, what we're going to do here is we're going to take our doubly linked list, and I'm going to call this node here the end. And I'll move this up so that you can see the text there. I call it end, well, because the actual name for it would be a sentinel. And sentinel is just a name I don't like to have to type in for my variables all that often. So I go with the end. Why the end? Because it's both the beginning, the first element, and the last element in a way. I make this list circular, and I make it so that the first element points to end, and the last element points to end. So end is the previous of the head, and it's the next of the tail. And then, of course, to make my links complete, it points up to the first element, oops, and it points to the last element. So end.next, whoops, and I guess these should be off of the other sides. End.next is the head of the list, and end.prev is the tail of the list. So I am keeping a head and a tail, but I'm keeping them kind of implicitly, okay? Not in an explicit form. Okay, so now we want to write our code for doing this. So we'll bring up Eclipse, and inside of our ADT package, we will go ahead and make a new Scala class, and I'll call it Mutable DLL. It turns out the code that we're writing here is close to code that would actually be used in libraries. You don't generally implement a standard linked list as singly linked because of the complexities of the head and tail. If you're going to have a linked list data structure, for example, a list buffer, then you typically do it by writing a doubly linked list, and you write a doubly linked list with a sentinel. Now, to start things off here, I'm actually going to go ahead and just paste in the code that we had for our singly linked list. Hey. Okay. And now do imports. Can't find that type of import. Collection.mutable. And okay, so technically this has no errors because this is exactly what the singly linked list was doing. But I'm going to get rid of the body of most of these functions. Maybe I'll keep some of the things around that have a num element. We'll come back and we'll play with these things. I no longer have a head and a tail. That'll introduce a whole bunch of errors that we'll have to fix. And my node now has a data and a next, and it also needs a previous. Okay. So we have our 2 pointers as well as the data. What happens when we do and then we have a num elements. What happens when we do an append at the end? Okay, so we're throwing something at the end of our list. Well, in this case, I need to put it after the tail. Oh wait, I need to put in a declaration here. Private val end equals new node. And this is where things get a little bit challenging. So let's think of our initial conditions here. Okay, turns out the end node, the sentinel node, has one minor challenge to it, which is what data do you store there? Because it turns out you don't really need to store any data. You kind of want to leave it as blank. That can be, this is a little bit of a challenge because, okay, well, 0, no, null, no. This is that same problem that we had with our stacks and our queues in that we don't know the default value. I don't know a default value for A. Well, I can get a default value. I feel like this is not the most efficient way, but it works. And now when I do that, I just need to add a manifest. So I pass in a manifest. Our end node, I create an array of size 1 so that you can read this. Note, it does that first. It makes an array of size 1, and then it pulls off the first element. So that will pull off whatever the default value was. After having this end, though, I need to make sure that my list is circular. So end.prev equals end, and end.next equals end. Okay. My num elements is going to do what it does. Let's go down and let's look at some of these easier methods. Okay. This method changes. This needs to go back to our initial conditions. End.prev equals end, end.next equals end. So have the node wrap around and point to itself on both sides and set the size to be 0. The length already works. Okay, I think the next easiest one is the append or the prepend. So our tail pointer is end.prev. Okay. And what I need to do is I need to make a new node. And this new node is for its data. It's going to have what was passed in, elem. Its previous is going to be end.prev, and its next is going to be end. Because we are adding to the end of the list here, this is adding a new node over here. I want to have it so that its previous pointer points back to there, and its next pointer points to the sentinel. So that's what I've done here. And then what should point to this? Well, there are actually 2 pointers that need to point to this. One of them is this pointer will need to be updated to point to the new node, and then also this pointer will need to be updated to point to the new node. So I need to reset both of those pointers. I can't do both of those in one line here in Scala, but I can do one. I am actually going to choose, well, here, I could introduce a new variable. Actually, let's go ahead and introduce a new variable. Val in equals, I think it's just easier to read the code and probably for you to understand what's going on. So I give a name to that variable. And then I can say end.prev.next equals n, and end.prev equals n. Okay, so let's think about that a little bit. Back to this drawing. N's previous is this, and its next is here. So that's changing this pointer and pointing it to the new node that we created. And then the other line was n's previous, this arrow right here, point it to the new node as well. So we change our two pointers and link in that new node. What about and notice there is no special case for head or tail here. That's the advantage of using the doubly linked list with a sentinel. Okay, it's that sentinel, it's this end node that makes it so that all the pointers are either previous or next. Okay. They're really, it greatly simplifies the code, and you'll see that even more in some of these other methods. So what about when I prepend? Well, now I'm going to build a new node. Its previous pointer is end, and its next pointer is end.next. I gave it a name here, and now I want to change ends next prev to point back to the new node, and ends next to point to the new node. So in this case, I'm doing my insert over here at the beginning. So I make a new node, it needs to point to this first element, and it needs to point back to end. And then then we need to reset and have this one's previous point back and have ends next point to the new node. And that is exactly what we've done here in the code. By the way, if you haven't noticed this yet, it is highly beneficial when you are working through code with linked lists to be drawing these pictures. They can be very helpful in figuring out what's going on. So what about the apply method? I still want to throw an exception here, but now I don't have an HD. What is the equivalent of my head? Well, it's end.next. So I start off at end.next, I run the same for loop, and I return the data. And we're done. We've already modified clear. Last time, after we did apply, we said, well, the next easiest thing to do was update. So once again, our head is end.next, and the rest of the code stays the same. Okay, so yay, okay, those were easy. In those cases, because I'm not moving any pointers, the singly linked list, the code wasn't that complex, and so it doesn't get any simpler or harder, really, in the doubly linked list. What about remove? Okay, so we still need to decrement the number of elements, but previously we had this special code for what to do when the thing was empty. I'm going to take out that special code. I don't want it anymore. Now I'm going to say, I want my rover to walk, and I'm going to take my rover and walk it all the way to the thing that I'm removing. So I mentioned earlier, the other advantage of this doubly linked list is that I can go to a node, and from that node I can remove it because I can go back and find this pointer and route it around, and I can go forward and find this pointer and route it around. I don't have to stop one shy. So I start at end.next because that's the equivalent of my head, and I don't stop one shy. Ret equals rover.data, because I actually went to the node that I want to remove. Sometimes I refer to this, instead of using rover in these few circumstances, I'll occasionally call it victim, because it's the thing that I'm taking out of the list. And now instead of so I don't need this special case. This was a special case that dealt with tail. I don't need that, but I do need to reset two pointers. So one, I don't need to actually set the rover's next or the rover's previous, but I need to set rover's next .prev to be rover's prev, and rover's prev.next to be rover's next. Let's look at what that would mean in the code. if this is rover, this one we're removing, rover's next prev is this arrow right here. I don't want it pointing to there. I want to grab it and make it point all the way over to here. And then I take rover's previous next, which is this arrow right here, and I make it point to rover's next. So if we go back and we look at the code, rover's next prev points to rover's prev, and rover's prev next points to rover's next, which does exactly what we just did here. And now notice that the links completely skip over this. This node still links to the others, but these are one-way links. And so nothing refers to this node. It is impossible to reach this node now, and it's trash. And the garbage collector will come and pick it up after we've done that. Okay. So that's the remove method. Now hopefully in this case, you can clearly see this code got shorter. Okay, that whole block for what to do for the for when you were deleting element 0 went away. And while we did have to reset 2 pointers, it turns out I had to have a thing down here with an if to check for the tail anyway. So iterator. Iterator is actually really easy. In dot next. That's the only change. Wait, nope, that's one of the 2 changes. The other one is here. Okay. We stop. Interesting thing to note about this list, there is no null. Okay. None of these references are null. They all point to something. So we got rid of all of our null references, so clearly we shouldn't stop at null, otherwise we will keep going forever and ever. We stop when rover gets to end, okay, because that means that we've passed beyond the end of the list and we're at the sentinel. Okay. That's only one method now has errors in it, and that is our insert all. Once again, our insert all had this special case in it. And I am just going to go out on a limb and say, you know what? I don't need a special case for that anymore. Okay. So I'm going to delete it. And then I want to see how we can fix this. So once again, instead of head, it's in.next. Instead of n-1, I'm going to go to in, and that way rover is not at the node prior to what we're deleting. It is at the node, or well, it's not at the node prior to where we want to insert things. It's at the node where we want to insert things. So in other words, if I was inserting index 1, this is index 0, this is index 1, my rover is actually going to be sitting right here. And that actually works very well because every node that I insert should be inserted before this rover. If I stopped rover here, well then the rover has to keep moving forward, which is what we did for our singly linked list, but I don't have to do that for my doubly linked list. So let's go ahead and just, once again, because I think it might be a little bit more clear, let's go ahead and let's introduce a new node in, which is the data, the element that we pulled off of our traversable here. And how does it link in? Well, its previous pointer should be rover.prev, and its next pointer should just be rover. Once again, I am inserting my rovers here, and I want to insert before this. I want to insert things that take over this index, so this is where the stuff will go, which means that I want to have an element that's in here, its previous points to the previous of the rover, and its next points to rover itself. Okay. I increment the num elements, and now I need to reset my other 2 pointers. So one of those pointers is rover.prev.next equals in, and the other one is rover.prev equals in. And we can look in our drawing. So I've just created a new node here, and I want to say rover's prev's next. This arrow right here points to the new node, and then rover's prev right here points to the new node as well. Let's make sure that's what I actually said. Rover's prev equals the new node. So that creates a new node and links it in, and the question is, does it work for the next loop through? Well, rover hasn't moved, so rover is still the node that we're inserting in front of. So we make another one of these, and it now points to rover's prev, which, based upon the last time through, we set to be the node that we had just created. Okay, and so the next item will link back to the one that we had added before it. Boom, 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 all of those work, and I no longer have the special case because there is no more special case for the tail. And that's it for the insert all. And I'm going to stop this video here. We have written a doubly linked list with a sentinel. Hopefully you see how that sentinel helps us removing a lot of special cases. Of course, this code is still complex enough. I need to test it before I actually feel confident that it's good.